All right, let's talk about how you're going to categorize or predict a general mix of chemical reactions. So let's start at the beginning. So for each of these, we're going to predict the reaction, balance the reaction name, the reaction type, and if written with words, rewrite as a chemical equation. So predicting or determining the reaction type is actually one of the first things we want to do because it tells us kind of what we have to do with what we're given. So I look at this one, and how do I recognize the reaction type? Well, it is an element in a compound. However, instead of single displacement reactions, which is not what we say for element and compound, I notice this is oxygen. Any compound reacting with oxygen, that has a special name. It is combustion. And so, well, if it's combustion, then we got to understand that anything containing carbon will combust to produce carbon dioxide. Anything containing hydrogen will combust to produce water. So, given that, we can then go through and, okay, we predicted the reaction, name the reaction type, let's balance it. 12 carbon, make 12 carbon. 22 hydrogen. Okay, 22 hydrogen, we got to put an 11 here, that makes 22 hydrogen. Finally, what are we going to do with those 11 oxygens, 12, 13 oxygens? What do we have here? We've got 11, and then this is 24. So 24 oxygens here plus 11 oxygens here equals 35 oxygens on the product side. So we need to get 35 oxygens on the reactant side. So if we have 11 already, we have 35 that we need minus 11 equals we need 24 more. So we just need to get 24 oxygens out of here. We can do that by putting 12. So it turns out that's actually it. We've balanced it. Let's double check on that. 12 carbon, 12 carbon. 24 oxygen plus 11 more makes 35. 24 oxygen plus 11 more makes 35 oxygen. So that's it. We successfully balanced it. That's it. All right, onward. Now this is reacting with oxygen, so it's combustion. However, it's also a pure element reacting with oxygen, or shall I say it's two pure elements reacting, so we can also call it synthesis, especially because it only produces one product. That's a synthesis thing. When two things combine to make one, that's a classic synthesis. All right, so given that, well, it's already given us the answer, so let's go ahead and just check for balancing, Fe2O3. So I'm going to put I do notice like the iron is easy enough, but the oxygen, there's a 3 here, there's a 2 here. So let's take my little trick, put a 2 right here, and take this 3 and put the 3 right here. That way you have 6 oxygen, and 2 times 3 is 6 oxygen. And 2 times 2 is 4 iron, so we put a 4 right there, and there it is. We've successfully balanced it. All right, that's that. Onward. Calcium hydroxide and phosphoric acid react to make water and calcium phosphate. This is compound plus compound makes compound plus compound. Ladies and gentlemen, this is a classic double displacement reaction. If you put double replacement, that's just as fine. Okay, so let's do it. We've got it already given to us in the products. We just got to balance it. So where do we start? Well, there's no pure elements to save for last, so we just jump in there. Let's see. I guess I can start with calcium. Why not? So it's 3 calcium, so I can balance that with the 3 calciums. Okay. Let's see. Hydroxide. Oh, there's no hydroxide over here. However, there is... what are we going to do with all these oxygens? Okay, so we need to address something. There's oxygen here and there's oxygen here. But you'll notice this is part of the polyatomic ion phosphate, and this is also phosphate. So if you see a polyatomic ion, don't break it down into like phosphorus and oxygen, just keep it as a unit. So if I see 2 phosphates here, for example, I put a 2 because that makes 2 phosphates here. And what that means is when I'm counting these oxygens, because I already counted the phosphates as a separate thing, don't go back and count these oxygens again, because then you'd be double counting them, and you don't want to do that. So when I'm counting oxygens, because I already looked at the phosphates separately, I ignore the phosphate when counting oxygens. So this is 2 oxygens, but times 3, that makes 6 oxygens here. I need to get 6 oxygens here, oh boy. So I'm going to put a 6 here. All right, now, is that going to work with the other stuff? What about all those hydrogens? That's 12 hydrogens. Well, that's 6 hydrogens right there, and then 3, this is hydrogen times 2 is 2 hydrogen, and then times that by 3 again. 2 times 3 is 6 hydrogen. So we got 6 hydrogen here, 6 hydrogen here for a total of 12. So it works. 3 calcium, 3 calcium. We have 6 oxygen and 6 oxygen. 6 hydrogen, 6 hydrogen. Sorry, 12 hydrogen, 12 hydrogen. And then 2 phosphate, 2 phosphate. All right, it works. That's our balancing. Let's do this also. All right, it is not this, but rather the fact that there is one reactant that tells us that this is decomposition. This just means the decomposition happens with heat added. There are certain decomposition reactions that do not occur, or that do not need heat to be added. That said, for this particular reaction, what does it turn into? Typically, decomposition will separate it into the elements it's made out of, but this is a special one. Metal carbonate will decompose to make a metal oxide plus CO2. And sodium and oxygen is a -2, sodium is a +1, so 1 oxygen, 2 sodium, so Na2O is the formula. And then we just balance. 2 sodium, 3 oxygen, there's 3 oxygen, 1 carbon, 1 carbon. It's already balanced as written. Done. All right, next thing. Calcium plus silver nitrate. This is a classic single displacement reaction with an element in a compound. An element in a compound, and it's a non-oxygen element. All right, so anyway, calcium will switch places with the silver because calcium makes a positive ion and silver makes a positive ion. That's why they switch places with each other. They are alike. They are both potential cations. So the calcium pairs with nitrogen and the silver comes out by itself. So let's put silver by itself and let's pair calcium with, and I think I said nitrogen earlier by mistake, I meant nitrate. Now calcium is a +2, nitrate is a -1, so your formula will have 1 calcium and 2 nitrates. So let's make that 1 calcium and 2 nitrates. And then, okay, so what am I doing here? Step 1 is I switch the pieces. So put calcium with nitrate, put silver by itself. Step 2, I'm fixing the formulas now. That is the correct formula for silver by itself. This is the correct formula for calcium plus nitrate. Step 3, balance. So 1 calcium, 1 silver, 1 nitrate, 2 nitrates. Oh, I better put a 2 right here, which means I better put a 2 right here. All right, there we go. Now it's balanced. 1 calcium, 2 silver, 2 nitrate, 2 nitrate. All right, let's move on. Zinc metal plus aqueous hydrochloric acid. So we need to figure out what is this type. So zinc metal is a pure element. Hydrochloric acid is a compound. Pure element plus compound is single displacement reaction. If you put single replacement, same deal, it's fine. So we need to rewrite this equation. So zinc metal is Zn, hydrochloric acid is HCl. Remember, hydro means no oxygen in the formula, and chloric means oxygen, contains chlorine, and then acid means it starts with H. All right, now let's see. So zinc plus HCl. And what's that going to be? It's a single displacement reaction. So zinc is positive, hydrogen is positive because it's at the start of the formula. So that means zinc and hydrogen will trade places. So zinc's going to bond with chlorine and hydrogen will be by itself. So let's put hydrogen by itself and then zinc with chlorine. So this was step 1. Switch the parts. We just did that. Hydrogen by itself, zinc with chlorine. Step 2, fix the formulas. The formula of hydrogen is H2. It's a diatomic element. As for zinc plus chlorine, zinc is a +2, chlorine's a -1. So that means 2 chlorines and 1 zinc in the formula to be like that. So step 1, switch the parts. Step 2, correct the formulas. Step 3, balance the equation. So 1 zinc, 2 hydrogen, 2 hydrogen, 2 chlorine, 2 chlorine. That's it. All done. Next, we have two compounds reacting with each other. That makes it a double displacement reaction. All right, so what are we going to get? The lead's going to pair with the iodine. The potassium's going to pair with the nitrate. So potassium pairs with nitrate, and the lead pairs with the iodine. So that was the switch the parts. So anyway, now we got to fix the formulas. Potassium is a +1, nitrate is a -1, so 1 potassium and 1 nitrate. Therefore, this is fine. Now, what about lead? Lead's a variable charge. So if you have PbNO3, and there's 2 of them, each nitrate's a -1. There's 2 nitrates, so there's -2 charge. Therefore, the lead must be a +2 charge. So if you have lead that's a +2 charge and it's paired with iodine, which is a -1, you're going to get 1 lead and 2 iodines in the formula, which means PbI2. Okay, so that was step 2. Fix the formulas. Step 3, balance the equation. 1 lead, 2 nitrate, 2 nitrate, 2 potassium, 2 potassium, 2 iodine, 2 iodine. There we go. That's going to work. All right, next. Aqueous iron 3 bromide plus fluorine gas. Fluorine gas is F2. It's a pure element. So compound plus element, that is single displacement reaction again. Let me make sure that's in view. Yeah, okay. Oops, I don't know why I just wrote that down there. Sorry to the viewers. Reaction type. All right, I'll put the balanced reaction here. No need to do this on your own paper. That's just a mistake of me going too fast and not paying attention to what I'm doing, apparently. So no need to switch the order on your paper. Anyway, it's a single displacement reaction. So that means, let's write out what's going to be happening. Iron 3 bromide, Fe3+, and then bromide. So that's 3 bromines, 1 iron. So FeBr3 plus fluorine gas is F2. And we got to follow our steps. So step 1, switch the parts. Now don't try to switch iron and fluorine. They're not alike. Iron makes a cation, positively charged. Fluoride makes a negatively charged anion. So the pure element switches places not with iron, but with bromine, because fluorine makes a minus ion, bromine makes a minus ion. They are alike. So fluorine and bromine switch places. So fluorine's going to attach to iron, and bromine's going to be by itself. So the iron is going to attach to the fluorine, and then bromine will be by itself. So that was the switching the parts. So iron with fluorine and then bromine. Next, we fix the formulas. Bromine's a diatomic element, so Br2. Now here, iron 3 bromide, we assume that iron remains a +3 charge. So if iron has a +3 charge, and you put it with fluorine, fluorine's a -1, so you have 1 iron. Iron's a +3, so you have 3 fluorines. So FeF3. So if that's how it's going to be, then we can balance it. So there's, oh, look at the, okay, that's a little complicated. What do we do? I take this 2 from the bromine, and I put it here. I take this 3 from the bromine, and I put it here. So 2 of these make 6 bromines, 3 of these make 6 bromines, so 6 bromine, 6 bromine. That's good. I'll do the same with the fluorine. I'll take its 3 and put it here. I'll take this 2 and put it here. So 6 fluorine, 6 fluorine, and oh, check it out. By doing that, 2 iron, 2 iron. So that problem solved itself. Okay, so 2 iron, 2 iron, 2 iron, 6 bromine, 6 bromine, 6 fluorine, 6 fluorine. It's good. It's done. It's balanced. Next. Solid potassium chlorate. Just one reactant, so you're going to assume that is a decomposition. All right, with heat added, by the way. That's what that triangle is, as a reminder. Anyway, solid potassium chlorate. Potassium is a K+, chlorate is ClO3 with a minus charge. So 1 potassium, 1 chlorate in the formula. That's KClO3. Don't forget the little triangle delta up there. Technically that triangle is called delta. Anyway, so it's decomposing, and a metal chloride decomposes to the metal oxide and the, oh, sorry, my mistake. Not a metal oxide. It decomposes to the metal chloride and oxygen gas. Remember, oxygen, pure oxygen is an O2. As for the metal chloride, potassium is a plus, Cl is a minus, 1 potassium, 1 chlorine, so KCl is the correct formula. So what do we got here? We got 1 potassium, 1 chlorine, 3 oxygen, 2 oxygen. Oh, that's not good. So I'll put this 3 right here. I'll take this 2 and put it right here. That makes 6 oxygen and 6 oxygen. That also makes 2 potassium. So I put that 2 right there. It also makes 2 chlorines, and we have 2 chlorines. So there we go. It's good. All right, that's what it looks like. Okay. Write the balanced equation for the decomposition of barium hydroxide to make barium oxide and water. Okay, actually that gave you almost all the info you need. Decomposition. It didn't say heat added, so I'm not going to add the little arrow or the little delta over the arrow. I'm just going to say, let's see, even though in reality it does, if it doesn't tell you heat added, then you just don't assume. All right, so barium hydroxide. By the way, barium is a 2+, hydroxide is a 1-, so the formula would be 1 barium and 2 hydroxides. So barium and 2 hydroxides. Remember, 2 polyatomic ions. If you got more than 1, you got to put parentheses. So that's going to decompose to make barium oxide and water. How do I know that's the form of barium oxide? Because barium's a +2, oxygen's a -2. When it's equal and opposite charges, it's 1 of each. And if you're having a hard time seeing that, that makes Ba2O2, which simplifies to BaO. All right, so anyway, that's that. 1 barium, 1 barium. This is 2 oxygens. That's 2 oxygens, 2 hydrogens, 2 hydrogens. Its balance is written. That's it. All right, next. Synthesis reaction that would be needed to produce potassium nitride K3N. Well, synthesis. Don't get lazy, write it out. All right, same thing here, don't get lazy, write it out. Balanced reaction. Remember, synthesis is 2 things coming together to make 1. So if it's potassium and nitrogen, that means pure potassium plus pure nitrogen makes K3N. So pure potassium plus pure nitrogen makes K3N. Now remember, nitrogen's a diatomic element, so put a 2 right there. And then as for this, all right, this potassium right here, that is the formula for pure metallic potassium. All right, so what do we got here? 2 nitrogen. All right, well, we got to have 2 nitrogen. And that makes 6 potassium, so we got to have 6 potassium. Well, there we go, ladies and gentlemen, that takes care of it. All right, now, next. The balanced equation for the combustion of isooctane. All right, so how are we going to deal with this one? You are going to know that combustion, yes, combustion, means reacting with oxygen. So that means C8H18 plus oxygen. It contains carbon, therefore one product is CO2. Contains hydrogen, therefore another product is H2O. Now we got a balance. 8 carbon, 8 carbon. 18 hydrogen. We got to put a 9 there to make it 18 hydrogen. Okay. How's that going to turn out? So how many? So it's 8 carbons, 18 hydrogen, 18 hydrogen. So far, so good. 2 oxygen here. And we have 16 oxygens here. Plus 9 equals 25 oxygens. Okay, we need to get 25 oxygens out of this. And there's 2 in every molecule, so we need 25 halves O2s. That's 12.5 oxygen, or 12.5 O2s. So what we then do is, well, we can't have a fraction, so we're going to have to times everything by 2. in order to make that fraction go away. So 25 halves times 2, or alternately phrased, 12.5 O2s times 2 makes 25 O2s. And then when you times everything by 2, that means this 8 becomes a 16. And this 9 becomes an 18. And we double check to make sure that worked. 2 times 8 is 16 carbon, 16 carbon. 2 times 18 is 36 hydrogen. 18 times 2 is 36 hydrogen. 25 times 2 is 50 oxygens. Now we have 16 times 2 is 38 oxygens plus, 16 times 2 is 32 oxygens. Need to work on my math there. 18 more oxygens equals 50. So we have 50 oxygens on each side, therefore it checks out to be correct. All right, that's done. Now, next one, coal, consisting primarily of pure carbon, whose formula is written simply as C, is used to extract iron from iron ore. Write the balanced reaction for the production of iron from coal and iron ore. Hint, carbon dioxide is the other product aside from pure iron. Okay, so coal is pure carbon. So what's going on here? We have reactants and products. Let's categorize things here. Reactants. Okay, it says from coal and iron ore, you're using these as your starting products. So coal, it says primarily pure carbon, so let's just C. So that's one reactant. And then extract iron from iron ore. That means you start with iron ore. That means this is our other reactant, Fe2O3. What do we produce? It says producing of iron. That means Fe is a product. And then it says carbon dioxide is the other product, which implies that there's only two. So reactants are carbon plus Fe2O3, products are iron plus CO2. So in other words, we have an element plus a compound react to make an element plus a compound. This should be pretty clear that it is a single displacement reaction. All right, well then let's do the single displacement reaction. Carbon plus Fe2O3 makes iron plus CO2. Let's balance this thing. All right, we'll save the pure elements for last. So carbon and iron, let's do the oxygen first. So there's 3 and 2, so let's put this 3 over here, and let's put this 2 over here. So that's 6 oxygen, 6 oxygen. So 2 times 2 is 4 iron, and 3 carbon, so I'll put 3 right there. So let's just double check. 3 carbon, 4 iron, 6 oxygen, 6 oxygen. Okay, it's good. That's it. That's the balanced reaction. All right, let's do this last part. Fermentation of fruit juice to produce wine involves the conversion of glucose to ethanol and CO2. Write and balance the equation. All right, conversion of glucose, that means we start with C6H12O6, and we convert it to, that means we produce C2H5OH plus CO2. And it says, write and balance the equation. All right. Well, we've written the equation. Now how to balance it? Carbon is present in multiple molecules. That's complicated. Let's not do that first. Oxygen is present in multiple molecules. That's complicated. Let's not do that first. Hydrogen is only present in 2 molecules. Okay, we can start with that. All right, so there are 6 hydrogens here. Don't forget, 5 plus 1 more makes 6. So 6 hydrogen, and here we have 12. So I need to multiply this by 2 in order to make 12 hydrogens here, because now I got 12 hydrogens here, and it matches. Okay, that's a good start. Now how about the rest? Carbon. Ooh, hey, this could be good. Check it out. This is 4 carbons. And then this makes 5, so we have 6. And then this is, what about the oxygens? We have 2 oxygens, and then 2 more for a total of 4. What can we do to make this work? Well, I need to add, I've got 5. What if I put a 2 here? That would make 2 times 2 is 4 carbons. 5, 6 carbons. That makes 6 carbons. Because if I increase the number of carbons here, then I'd wind up with like messing up the hydrogens, which matches this up, which messes this up, which messes this up. You'd wind up in an endless circle. So the hydrogens were good here, so I'm going to change the number of carbons over on this side. If I make it a 2, I've got 6 carbons on this side, 6 carbons here. So now hydrogen is good, carbon is good, and what about the oxygen? And there's 6 here. So this is 2 oxygens, and this is 4 oxygens. And 2 oxygens plus 4 is 6. So it works. It's actually completely balanced. We just did it. All right, that is a properly balanced equation. And that concludes the worksheet. Well, there you go, ladies and gentlemen. Happy studies.